Okay, so here we're going to do an extension and work a little bit further on our combinations. Okay, and these again are choosing elements from a particular set of items, or choosing multiple elements from multiple sets of items. But the key is that position is not important, ordering is not important. So rather than choosing president, vice president, secretary, you're just choosing a group of three. Okay, and we're going to elaborate on this idea. Okay, and use some different strategies and work through those different strategies. Okay, so this is problem solving with combinations involved. And then we're going to look at a specific type of problem where we actually don't pick a definite amount. Okay, so every combination question that you did for your homework, you probably had a specific amount that you were looking for. Okay, in this case, we don't. All right, and so there's an approach that we can take, and I'll do a comparative approach to understand all the different ways in which we can look at it so that we can understand how to approach it. Okay, so first we start with just a problem that has some interesting principles to it, and there's multiple ways in order to do it. Again, for those of you guys who are in day school, this is the appropriate section. If you're using the new textbook and if we have normal school, okay. But if we have online schooling, then we're not going to be using this. Instead, we'll be using section 5.3. Okay, so that's one small difference that could exist there. All right, so let's look at this scenario here. A band can play 5 rock songs, 2 blues songs, and 3 jazz songs in their repertoire. How many ways can the director choose 3 songs? Which isn't too bad, right? You add up all the songs and do a choose 3. It's not too difficult. But again, we put a little qualification on here, a little condition. Choose 3 songs if he wants at least one to be a jazz song. Okay? So how many ways can the director choose 3 songs if he wants at least one to be a jazz song? So of the 3, you could have one of them be a jazz song, 2 of them be a jazz song, or 3 of them be a jazz song. Okay? So really what we have are rock songs, which we're not too concerned about in this question. Blues songs, not too concerned about. And then jazz songs. Okay? And that is something that we're concerned about in this question. So we have a total of 5, 2, 3, 10 elements. Okay? And so if we were to draw that, we'd have rock songs, blues songs, jazz songs. So we could go 10 here if we wanted to, and those are all the songs. And then we want to play a small subset of 3. And if we were just choosing songs, it'd be just 10, choose 3. It wouldn't be difficult. But in this case, what we're doing is having at least one jazz song. So I'm going to break this up into 3 scenarios. I'm going to go 1 jazz song. Okay. And if I have 1 jazz song, then that means I have jazz songs that I choose from, and then I have others. Okay, which are basically the ones that aren't jazz songs. So we've got 5 plus 2, 7 other songs, other types of songs, and 3 jazz songs that we can choose from. And in this case, if it's 1 jazz song, we're going to choose 1. Okay, and so 1 jazz song would be a 3, choose 1. And then, of course, we have to choose 3 in total, so we need to choose 2 of the others. 7, choose 2. And you can see that we're totaling 1 plus 2 is going to give us 3. Okay, now because we're choosing jazz songs and the other songs, we do a multiply. And so that ends up looking like 3. 7 choose 2 is 7 times 6 is 42 divided by 2, 21. Okay, so that means there's going to be 63 ways to choose 1 jazz song. Okay, then we also have the situation of 2 jazz songs. And the number for that one is going to be, in this case, it would be 3, choose 2. Okay, so 3 jazz songs, we're choosing 2 of them. Okay, and that must mean, of course, that we're going to have to, of the 7, only choose 1 of those to get a total of 3. And because we're choosing jazz songs and the other songs, okay, then we're going to have 3 of them there. So 3 choose 2 is actually 3 as well. 7 choose 1 is actually 7, and we get 21. So that's 2 jazz songs. Okay, it did say at least 1, and the maximum we can have is 3 out of 3. Okay, because we're only choosing 3 songs, and we only have 3 jazz songs to choose from. So we could go 3, choose 3. Okay, so 3 jazz songs. And the number there is equal to 3, choose 3. And then 7, we're choosing 0. Again, we have to total up to 3. You don't necessarily have to do 7, choose 0, because 7, choose 0 is just the number 1. There's only one way to do that, choose nothing. Okay, and we're choosing jazz songs and not jazz songs, so 3 times 1, or 3. Now, what do we do with this? We've got 1 jazz song, we've got 2 jazz songs, we've got 3 jazz songs. How do we do at least 1? Well, then we add the 3 of them up. So So the number with at least one jazz song is going to be 63 plus 21 plus 3, which is a total of 84, 87. Okay? I don't even know if I actually calculated that otherwise, but 87 different ways that we could choose at least one jazz song. Now there's another way. Okay, there's something called the indirect method, which we've sort of seen as we've been going along. Okay, and I'm sure when we were taking up questions with permutations and combinations, we tried the indirect method. How do we do the number of ways in which someone's together, number of ways in which someone's not together? That's sort of an idea. So in this case, what we could do is we could take the number of ways that we have at least one jazz song. And what we would do is we would take all possibilities, jazz songs, no jazz songs, everything, minus the ones where we have no jazz songs. And if we do that, if we take all the possibilities and we remove the ones where we don't have any jazz songs, then we're going to have ones that have at least one jazz song. So if we're going to do all of them, that would just be all of the songs. 10, choose 3, because remember you're choosing 3 songs for their set list, right? Choosing 3 songs. And then you'd subtract no jazz songs. Well, if it's no jazz songs, then it's going to be my 7, choose 3. And in that result, I've got 10, choose 3. 10, choose 3, okay, which is 120. Minus 7, choose 3, which is 7. Choose 3 equals 35. And then that minus that is 85. Is it 85? 85. Why is that 87? 63, 21, and 3. 21's 24. That's 87. Why is that different? I don't know why that's different. Oh, 3 choose 3 is 1. And that's 1. And this should be 85. My mistake, guys. Again, my mental arithmetic is off. Okay, and so they both agree with each other that there's 85 ways to choose at least one jazz song. So whether you do it directly and you break it up into 3 cases and you add them all up, or whether you do it indirectly, whether you take at least one jazz is all of them minus no jazz, and then we get the same scenario. So that's, again, problem solving. It's the left or the right more correct, one more correct than the other. No, they're both beautiful. One may take a little bit more time to do, okay? And if we were choosing 10 songs and we had a lot more songs in our playlist, it may be a bit faster to do that one. But either way, you'd still get there, okay? And you still get that correct, okay? So again, problem solving involving combinations, okay? So this case, it has our fundamental multiplicative fundamental counting principle. It has our additive fundamental counting principle. Okay, and here it has an indirect method that has to do with, I guess, sort of an additive subtractive method or a different approach that relates to, again, combinations and problem solving involving that. Okay, now in this one, remember, I'm choosing a definite number of songs. I'm choosing 3. But in this one, it's a little bit more abstract. Here, an artist has a pear, an apple, and an orange. How many ways can he choose one or more pieces of fruit for a picture? Okay, and of course what we can do is we can break that up into pieces, and I'm going to break that up into pieces in a bunch of different ways. First of all, I'll literally list it, okay? So if he's got one piece of fruit, because remember it's one or more, so we'll break it down into one piece of fruit. There's a pear, an apple, and an orange. So he could have a pear, okay, he could have an apple, or he could have an orange. That totals to 3 possibilities. 2 pieces of fruit. He could have pear apple, he could have apple orange, he could have pear orange. So that's also 3 possibilities. You could also have 3 pieces of fruit. In this case, you can go, well, you just have to have apple, orange, pear. There's no other types of fruit that you can have. So in that case, there's only one of those. And you can have 1 piece or 2 pieces or 3 pieces, which totals to 7. Not too crazy. Now, of course, we don't want to be able to have to list every single one. That's not an effective problem-solving strategy, so we want to look at it another way. What's another way? Well, if we want to keep in line with doing 1 piece of fruit, remember that we have 3 pieces of fruit, but we aren't choosing a definite amount. That's the thing that's variable here. So this could actually be 3 pieces of fruit, and I'm going to choose 1. This could be 3 pieces of fruit, and I'm going to choose 2. Now here we were definitely choosing 3 songs. So we saw the songs come from different places. Here we have the same amount of elements, but we're choosing different amounts of each. Okay, and so that's how this is a little different. For 3 pieces of fruit, it'd be 3, choose 3. And because we have 1 piece or 2 pieces or 3 pieces falling into the category of 1 or more pieces of fruit, then we would add those guys together. 3 choose 1 is 3. 3 choose 2 is 3, and then 1. So that's a little bit quicker of a way for us to do that, okay? And that's sort of the same strategy that we used over here, except here we're not choosing a definite amount. We're choosing 1 or 2 or 3. Here we were choosing 1 or 2 or 3 of jazz songs, but we were still choosing a total of 3 songs, so it's a little bit different. There's another neat approach that we can take that kind of goes along the line of this. And that is what I do is I look at each element, each piece of fruit, and I decide if I want to have it in the photo or not, okay? So in this case, if I look at the pear and I ask myself, hey, do I want it or do I not want it? Yes or no? Yes to the pear or no to the pear? Okay, so that means there's 2 possibilities in that scenario. In this case, I also look at the apple. And when I look at the apple, I say yes or no. Do I want an apple or do I don't want an apple? So those are 2 situations that can exist. And then I could say to myself, well, what about the orange? Do I want an orange or do I don't want an orange? Which is a 2. Now, what do I do with these circumstances? Well, when I'm deciding how many I'm putting in my whole photo, it could be yes or no for the pear, and I have to ask yes or no for the apple, and I have to ask yes or no for the orange. So it's 2 times 2 times 2. Now, we already know the answer. It's 7 and it's 7. But here we get the answer of 8. Why doesn't that work? Well, again, we have yes or no for the pear. That works. There's 2 possibilities. Yes or no for the apple. 2 possibilities. Yes or no for the orange. 2 possibilities. And we're asking the question about the pear and the apple and the orange. But what we didn't forget, or what we did forget about, was the fact that what if I said no to the pear, no to the apple, and no to the orange? It has to be 1 or more pieces of fruit. So I couldn't say no, no, no. So I have to subtract 1 from that circumstance. As a result of that, okay, I create sort of a new formula. And the new formula for the number of ways in which you could do something where you're not choosing a definite amount is equal to 2 to the n minus 1. 2 to the n is a yes or no for all elements. And n is the number of elements. So we have 2 and 2 and 2 and 2. If we had 5 different types of fruits, we could say yes, no for the first, yes, no for the second, yes, no, yes, no, yes, no. And it'd be 2 to the 5 minus 1. But in this case, it's 2 to the 3 minus 1. 2 to the 3 is 8. Of course, you have to use bed math, so you evaluate this first. 2 to the 3 is 8. Then you subtract 1, and what do you get? The correct answer, which is 7 ways. So when I look at individual unique elements and I don't know how many I'm going to pick, I could say yes or no to each one. Now you may say to yourself, yeah, if you're looking at them, you make that decision. But if you're sticking your hand in your pocket and pulling something out of your pocket, I don't know, receipts for a day's worth of shopping in multiple different stores, and you throw your hand in your pocket and you pull out some receipts, you could pull out 1 receipt or all the receipts or 2 or 3 or 4, and you don't know which one it is. You're not making a conscious decision for them, but there is 2 realms of existence, whether you do have it or you don't have it in that circumstance. And so that is where the 2 to the n comes from. The minus 1 is what's called the null set. And the null set is no, 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 no for all of them, etc. Or 0, 0, 0, 0 of all the elements. And of course, in this case, we can't have 1 or more. If we put our hand in our pocket and we reach and grab some receipts, it's conceivable that if you put your hand in your pocket and you pull out something, maybe you don't pull out anything at all, in which case the null set is not included in that circumstance and you don't subtract the 1. So you have to ask yourself whether you include it. So what does that look like as a formula? So when you want to choose some or an indefinite amount of a group of elements, okay, you're making a smaller group from a large group of elements and they're all unique and you want to take some of them, one way you could do it is the number of ways is to go n choose 0 plus n choose 1 plus n choose 2 plus n choose 3. So you can get 0 of them, 1 of them, 2 of them, 3 of them, all the way up to all of them. This would be all of them, okay? And then you subtract the 1. The 1 that you're subtracting is actually debatable whether or not you want to include it. Okay, so you could have a possibility of none. So I'll use that as in an example when we do our next one. This, and plus this, plus this, plus this, plus this, equals this every single time. Okay, as long as the n is the same as this n, then it's going to be the same thing every single time. And the minus 1 is if you can't have none of them. Okay, so that's that formula 2 to the n minus 1, when you have a bunch of unique elements and you're choosing a non-definite amount. Okay, it's like, you know, if you remember back when you went trick-or-treating, if you did, okay, and you go in to reach in your treat bag and you go to grab a bunch of candy, okay, you got like 1,000 candies in there, you could pull out 5 or 6 or 7 or 8 or 10 or 1 or 2 or whatever. Or like when someone says, hey, can I have some of your M&Ms or whatever? So you take the bag and you tilt it over. There could be 1 candy that falls out, there could be 2 candies that fall out, there could be 10 candies that fall out. In that case, you're dealing with a non-definite amount that you're choosing. Okay? And so as a result, it's something that could happen fairly often. All right? So let's apply this circumstance. Let's apply this formula. Let's apply this scenario. Now I'm going to have it up here for you guys on your good copy version of the note where I've got a nice, beautiful job done. And I want to flip here and I want to try some of these examples. Okay? So here's the scenario. Tommy's pocket has 1 penny, 1 dime, 1 quarter, 1 loonie. How many ways can Tommy pull out some change? So you got the change in your pocket. Okay, maybe not as applicable for ladies unless of case you get like a coin purse, because you guys don't have pockets. I don't know what that's all about, but whatever. For guys, you pull change out of the pocket. For anybody else, you pull something out of your purse, okay, or out of a change purse or coin purse or whatever it may be. Okay, so Tommy's pocket has 1 penny, 1 dime, 1 quarter, 1 loonie. Conceivably, you could reach in and you can get all 4 coins. You could also reach in and miss 1. It could slide between your fingers. Or you could miss 2 and 2 will slide between your fingers. Or maybe just grab 1 coin. But at least in this circumstance, because he's asking for some change, we're assuming that he's pulling out at least 1. It is possible to reach into your pocket or reach into your coin purse and actually have everything fall between your fingers. And as a result, you don't pull out any. Okay? But when we're approaching this, again, we have 4 elements. And we're choosing no definite amount. So when we have that, one way we could do that is, well, we could choose 1. We can't choose 0 because we're getting some change. So we have 4 elements, so it could be 4, choose 1, or 4, choose 2. I could get 2 coins. Or 4, choose 3, which means I get all the coins except for 1. Or 4, choose 4. Okay, that's going to be 4. And then or means plus. 4 choose 2 is 6. 4 choose 3 is 4. 4 choose 4 is 1. Okay? And then we end up with a number that is 4, 6, 15. So there's 15 ways that you could reach in your pocket with those 4 coins in your pocket and pull out something. Whether it's all of them or whether it's 1 or 2 missing or whatever it may be. Now, another way we could do that formula, is if you recognize it, is to use, we've got 4 elements, they're all unique, and we're choosing a non-definite amount. We can go 2 to the n minus 1. In which case, we go, the minus 1 exists because we're choosing some change, so we can't choose 0. And so it's 2 to the 4, because there's 4 elements, minus 1. 2 to the 4 is 16, minus 1, which of course comes out to be 15 ways. Okay, you don't have to answer it twice. I'm just showing you 2 ways to do it because there are 2 ways for you to do it. Okay, is everybody all right with that idea? Now in this circumstance, it's a little bit different, okay? And this is a little bit more like a practical situation because you usually don't have 1 of each of these coins. And of course, this is an old version because we got pennies. We don't use pennies anymore, okay? But in this circumstance, I'm going to move this out of the way because we're not necessarily going to need it the same as we would otherwise. Tommy got coins in his pocket again. He's got 1 penny, 2 dimes, 4 quarters, and 1 loonie. How many ways can Tommy pull out some change? Okay, well, I'm going to go to start from the beginning again to make sense of this because you can't do 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Because if you pull out 2 dimes, okay, more importantly, if you pull out 2 quarters, or if you pull out the other 2 quarters, it's still going to look like 2 quarters. So because we have elements that are identical to each other, okay, there's got to be a different way for us to do it. We can't use this choose scenario. It won't work. Okay, we'll either overcount or undercount the amount of ways that we can do things. Okay, so in this circumstance, let's go back to our first principles, the first way that we figured out the formula. So I'll say to myself, okay, for the pennies, what could I have? Well, I'm not going to say yes or no, okay, although I could for 1 penny. I'm going to say 0 pennies or 1 penny. So there's 2 options in that scenario. For the dimes, okay, we could have 0 dimes, we could have 1 dime, we could have 2 dimes. All of those possibilities exist. So there's actually 3 scenarios that could come across when you pull out some change. You either pull out 0 or 1 or 2. There's no more nor less than that could be in your handful. Okay, same thing for quarters. Although quarters, there's a lot more possibilities. You could go 0 or 1 or 2 or 3 or 4. So in actual fact, for 4 quarters, there's actually 5 circumstances. 1, 2, 3, or 4, or 0. Count them all up. 1, 2, 3, 4, 5 circumstances. So in that handful, there could be 4 quarters or 3 or 2 or 1 or even no quarters. You could miss them all. Last but not least, we've got our loonie. We've got 1 loonie, so we could either have 0 or 1. Okay, you could have a loonie or not have a loonie. And so there are 2 circumstances. And because for the pennies, there has to be a circumstance, and for the dimes, that same circumstance, and for quarters, and for loonies in 1 handful, because in 1 handful, it's 1 go. It could have pennies, dimes, nickels, or dimes, quarters, loonies. It could have 0 of all of them. Now, if it does have 0 of all of them, we did say how many ways could he pull out some change. So you can't have 0 of all of them. So what do we have? Well, we got 2 times 3 times 5 times 2. We can't use 2 to the n minus 1 because if we make this 2 to the 4, that would be 16 minus 1. And in this circumstance, it's not the way that it turns out. Sorry, it's not multiplying. Sorry, it is multiplying. Okay, because it's 1 and the other and the other and the other. So 2 times 3 is 6, 6 times 5 is 30, times 2 is 60. But if I was to go 2 to the 4 minus 1, thinking that there's 4 different coins, okay, then I would have 16 minus 1, which is 15. That doesn't work out with this scenario. And the other way that it doesn't work out is if I used, okay, well, I have what? 1, 2 is 3, 4 is 7, 5 is 8. 2 to the 8 minus 1. 2 to the 8 is 16 times 16, which is 256 minus 1. So in that case, it's too many. Okay. Remember, 2 to the n minus 1 is when all of my elements are unique. And for both of those, it doesn't work in this scenario. What we want to do is we want to go back to the definition of this 2 to the n minus 1 and where it comes from. And we can't do the chooses because we have identical elements. We have to figure out how we can get rid of or eliminate those identical elements. It's not as simple as in permutations. So how do I end up with this 60? And it's not 60. I have to subtract the 1 because I have to take away that scenario. So it's actually equal to 59. So how do I get 59 as an answer? Okay. Well, remember that for this one, it was yes or no, yes or no, yes or no, yes or no, right? Yes or no to the penny, yes or no to the 1 dime, yes or no to the 1 quarter, yes or no to the 1 loonie. But in actual fact, it's not yes or no. It's actually 0 or 1 for the penny. For the dime, it's 0 or 1. For the quarter, it's 0 or 1. And for the loonie, it's 0 or 1. So in actual fact, 2 to the n minus 1 and this circumstance work. When we have dimes and we have 2 of the dimes, then we can have 0 or 1 or 2. So that's 2 possibilities. That's the 3 possibilities. For the quarters, we've got 0, we've got 1, we've got 2, we've got 3, we've got 4, right? And that's going to be 5 possibilities. And the loonie is still going to be 0, 1, or 2 possibilities. And so that's where we get this circumstance for. What we can't have, of course, is 0, 0, 0, 0. So that's why we subtract the 1. And that's where this formula comes from. Okay? If I'm choosing at least one item out of a set of n items, the total number of groups that can be made from P identical items of one kind, Q of another, R of another, and so on. So if we have identical elements, we use this, P plus 1, Q plus 1, R plus 1, and we keep on going until we run out of elements. This would be for the penny. This would be for the dime. This would be for the quarter. And this would be for, well, the next one would be for the loony. It keeps on going. And then the -1 again is for 0, 0, 0, 0, etc. The null set. We take that away. Okay, so if we go back and use the formula for this, okay, use this formula, well, we have 1 penny. So it's 1 plus 1. And then we have two dimes. So it's going to be 2 plus 1. And then quarters we have 4, 4 plus 1. And then loonies we have 1, 1 plus 1. And then we always end off with the -1 if we're taking at least one item, which here we are pulling out some change. And so you'll see that the 1 plus 1 is 2, 2 plus 1 is 3, 4 plus 1 is 5, 1 plus 1 is 2. So again, when we're choosing non-definite amounts or variable amounts, this is really the formula that we use. This P plus 1, Q plus 1, R plus 1, and it will work for all, even if we have identical elements. It's just we're going to do a lot of 1 plus 1, 1 plus 1, 1 plus 1, 1 plus 1. Okay? So let's have a look at this scenario. Again, we're choosing non-definite amounts. So here's a question. There are 3 identical plates, 4 identical glasses, and 3 identical mugs on the dinner table. How many ways can I bring some, which means at least one item, to the sink? Okay? Well, we've got 3 identical plates. I could bring 0, 1, 2, or 3. So that will correspond to 4. Okay? Or we use the formula, 3 plus 1. For the glasses, I could bring 0, 1, 2, 3, or 4. So there's 5 outcomes there. Or 4, because there's 4 elements that are identical, plus 1. For the mugs, again, there's 3 mugs. And I could bring 0, 1, 2, and 3. Okay, so 3 plus 1. Okay, and then of course I subtract 1. The reason why is I have to take at least something. I can't take nothing back out. Okay, and so what I end up with, of course, is 4 times 5 times 4 minus 1. 4 times 5 is 20, times 4 is 80. 80 minus 1, 79 ways to bring at least one item to the sink and be a good citizen of the dinner table. Okay? All right. So that being the case, that's the circumstance where we choose non-definite amounts. We started off with choosing a definite amount, choosing 3 songs, and then we started doing things where we weren't choosing a definite number of songs. And we basically derived this formula that works for all circumstances. There's also 2 to the n minus 1, or n choose 0, n choose 1, n choose 2, n choose 3, n choose 4, all the way to n choose n minus 1. Okay, we can use those formulas for combinations. Again, problem-solving strategies, they work really well. Okay, here I've got some card hands, so I'm going to do a few of these card hands, and then I'm going to leave you be. I'm just going to give you 3 of those. The other ones, I'll let you look at the solutions and see if you can figure it out. Okay, so we talked about these already, so this is a repeat, but this is good problem solving. By now we have a full day's worth of homework and take up underneath us, and we're going ahead and working on these problems. So when I do these problems, again, I want a flush. Remember that for a flush, okay, we're going to have all of one suit. So let's make this, for example, hearts. Okay, and there's 13 of those guys, and I'm going to choose a 5-card hand. Well, if I have a flush, that means I'm going to be taking all from one suit. So in this case, all from hearts. Okay, so the number of ways in which I could do that would be 13, choose 5. Remembering, of course, that in a deck of cards, okay, it's a little bit more complicated. Okay, a deck of cards isn't so simple, okay, to remember off the top of your head. I told you guys, it'd be a good idea for you to go online and print yourself out a good one. Okay, this is the structure for a deck of cards. We've got 52 cards, 13 from each suit, diamonds, clubs, spades, hearts, 4 of each type, 4 2s, 4 3s, 4 4s, 4 5s, 4 6s, all the way up to ace. Okay, and so hopefully you remember that. All right, I'll have that maybe close by in case I need to refer to that. So this is how I choose a flush from hearts. But I could also have a flush from diamonds. I could also have a flush from clubs. I could also have a flush from spades. I could also have a flush from, what did I miss? I don't know. Okay, but all 4 suits. So that means that I've got 13 choose 5. That's the flush, all cards from the same suit. And then I multiply that by, well, technically it's 4 choose 1 because I'm choosing one of the suits. But most people will just say, I'm just going to multiply it by 4. Well, I can go 4 choose 1 here. And then in my next line, I'll go times it by 4. And I go 13, choose 5. That's my flush. 4 hearts. Choose 5 equals 1287. Then I multiply that by 4 because we can get flushes with just hearts, flushes with just diamonds, flushes with just clubs, flushes with just spades. And we get 5,148 hands are flushes. Okay, are flushes. Now what about 4 of a kind? Well, 4 of a kind is a bit different of a scenario. We have 4 of each type of suit, but we're grabbing 5 cards, right? So let's say this is 2s. Okay, I'm just talking about the 2s. So then it's going to be 4, choose 4. I can only choose 4 from 4, right? You can't choose more than that. So for 4 of a kind, 4, choose 4. And that's the 4 of a kind there. But how many different 4 of a kinds can I have? Well, I could have a 4 of a kind for 2s, or 3s, or 4s, or 5s, or 6s, or 7s, all the way up to aces. And there's 13 of those. Or if you want, you can do 13, choose 1. Okay? But then you have to say to yourself, yeah, but I need another card. Okay, I've got 5 cards here, right? If I've got 5 cards here, then what do I do? Right? What's going to happen there? Well, I've already taken 4 of these cards out and I've already used those 4 cards. So rather than having 52 cards in a deck, which is what I normally do, I actually have 48 cards in the deck. And I go 48 and I choose 1. 48, choose 1. Okay? Because I have to have 4 plus 1, 5 cards in my poker hand. 4, choose 4 is 1. 13 is 13. 48, choose 1 is 48. And so you'll find out that the 4 of a kinds, 13 times 48, there's 624 4 of a kinds. Okay? And that being the case, you know, you're finding a situation where you've accounted for all the cards that you're using. Okay? Again, more problem solving. Cards are a really good way to look at things because they're multiple groups, very stratified samples, really good ideas. I'm only going to do a few more of these. Let's do a full house. Okay? So a full house, if you remember what a full house is, it's a pair and a 3 of a kind. Okay? So let's say we take the 2s and we take the 3s. And we're going to take our 5 cards. So we're going to take 3 2s. Okay, that's going to be our 3 of a kind. So there's 4 2s, remember? So from those 4, we take 3. So it's going to be 4, choose 3. Excuse me. And, okay, how many of the different ones can I have? Well, I'll get to that in a second. We're also going to go ahead and finish off the card hand with 3s. Okay, we've got 4 of those 3s, and we're going to choose 2 of those. So we're going to go 4, choose 2. So that's my 3 of a kind, T-O-K. And that's my pair. Okay, that's my pair. All right. So I obviously have to have my 3 of a kind and my pair together. So I'm going to be multiplying these guys together. But how many 3 of a kinds can I have? Well, 2s is only one type. So there's going to be 13 different ones that I could have. You could have 3 2s, 3 3s, 3 4s, 3 5s, 3 6s, 3 7s, all the way up to 3 aces. Okay? Similarly, though, how many different types of pairs could I have? Well, if I'm taking 3 from the 2s, I can't have 2s over here, so I can't put another 13. There's actually 12 of them that you can have, because once you have your 3 of a kind, then your 2 of a kind, or your pair, is got to come from a different grouping. Okay, and here I have 2s and 3s, but it could be 2s and 5s, it could be 2s and 10s, it could be 2s and 11s, or sorry, 2s and jacks, 2s and queens, 2s and kings, and so on. Okay, so the 13 and the 12 are the types, the number of different types of 3 of a kinds, and number of different types of pairs. So 4 choose 3 is 4 times 13. 4 choose 2 is 6. And then 12 is just a 12, and we multiply all those guys together. 4 times 13 times 6 times 12. And we get 3,744 ways or different card hands that actually would give you what's called a full house. Okay? Now, the rest of these, 2 pair, a pair and only a pair, a 3 of a kind and only 3 of a kind, those are a little bit tougher. So what I'm going to do is I'm going to leave you with that. I'm going to do these, okay? But I'm going to leave you at that. I'm going to pause and say, you know what? If you understand up to that point, you're in beautiful shape. You can go ahead and get to work on the homework. Remember, your homework is not going to be this if you are online learning, if you're a night school or summer school student, okay? And even a day school student, but you're online learning, you're not going to be doing this. It's not going to be section 3.3. It's not going to be page 120. It's not going to be these questions. What it will be is, excuse me for a second, it's going to be 286, 1, 2, 4, 5, 6, 8, 10, 12, 13, 15, 17. All of those questions. Okay? All right, so I'm going to do a few more of these and show you what's involved in this scenario. Okay, let's try 3 of a kind and only 3 of a kind. And maybe I'll leave it at that and show you the rest of the solutions later on. Okay, so for those of you guys who are still with me, 3 of a kind. 3 of a kind's not too crazy to do. Okay, 3 of a kind's not nuts. Okay, what you have here is you've got 4 cards. Let's say it's your 2s. Okay, and you've got a 5-card hand, so you're going to choose 3 of those guys. That's your 3 of a kind. So it's going to be 4, choose 3. Just like we had in here when we had a full house, because a full house is a 3 of a kind and a 2 of a kind. Okay, but a 3 of a kind is just a 3 of a kind. That's it. Okay? Now, what happens, of course, is if I want to make it only 3 of a kind and nothing bigger than that, okay, remove all the 4 of a kinds and all that sort of stuff, I'm going to show you basically what you have to do. Okay, so I've got 4, choose 3. Now, how many different 3 of a kinds can I have? Well, can I have 3 2s, 3 3s, 3 4s? So there's really 13 of them that I can have. Okay, and that's not too crazy. It's 4, it's times 13. But what you end up having is a bit of a difficult scenario. Okay, because it's the other cards that you need to choose. The other cards that you need to choose. Okay, now you can eliminate the 4 of a kinds. Okay, but you can't eliminate the full houses, and you can't eliminate, well, full houses, and I guess what we call straight flushes, but those are a little fancier and so on. Okay, so that being the case, we need to have 2 more cards, right? Because we've got 3 already for our 3 of a kind, and we need 2 other ones. So we've got to choose 2. Now, if I take these 3 cards from the 2s, I could also have the next 2. So if I take 3 cards and I put 49 here, remember 52 is total how much I have in the deck. 52 minus 3 is 49. Then one of those cards is a 2. Okay? If I do that and I go 49, choose 2, then what I have to do is I have to take away all of the hands that are bigger than a 2 of a kind. And when I say bigger, they're more unlikely to happen, okay? By including that 49, choose 2, what am I including? Well, I'm including, if I have 3 2s, I'm including the 4th 2. Now, that would turn your 3 of a kind to a 4, choose 4, 4 of a kind. Okay, so I will want to subtract 4 of a kind from that to make sure that I can't have that. So I know that I calculated a 4 of a kind for you already. So I would want to look at 4 of a kind, and I want to subtract this calculation from it. Okay? What I would also want to do is I would want to take away also your full houses. And the reason why I'm taking away full houses is to only get 2 of a kind. You can't, if you have choose these 3 cards, you could be choosing from these guys, you could be choosing a pair. If you choose a pair, then it's a full house, and a full house is better than 3 of a kind. So you'd have to remove all the full houses when you do that. Now, when you have 3 of a kind or 2 of a kind or even a pair, you're not going to have a flush and you're not going to have a straight. And those are 2 that we haven't done yet, so you don't really need to worry. We did a flush, but flush all have to be the same suit. Well, if we choose 2 cards, 2 2s, one is going to be like a heart and one of them is going to be a diamond. Here we actually have 3, so we're going to have 3 different suits, minimum. So we don't have to worry about flushes. But you do have to take away what's higher than 3 of a kind, and that's 4 of a kind, and you have to take away when we have a 3 of a kind plus another one, which is a full house. If you take away those 2 calculations, so you take away that calculation and you take away from the previous page the 4 of a kind calculation, that's how you get a 3 of a kind only. And that's how you can understand that it can get pretty complicated pretty quickly. Okay, I'm not going to do the 2 pair and the pair. If you guys want me to take those up and actually do those ones, I can. I think on your problem sheet, I think I did a 2 pair. I did do a 2 pair. Okay, but pair and only a pair, I've got it sort of mapped out a little bit for you, the same way that I've got it mapped up for you there. Okay, so anyway, so have a look at that, see if it makes sense. But either way, we're all done. Okay, and those are much more difficult than what we're used to, but it's still something you may be interested in figuring out the number of ways in which that could happen.